So let's see if we can understand this kind of angular motion in a rather involved example. So we have a guy that's exercising in a fitness center, and he lies face down on a bench, and he's lifting weights with his one lower leg by contracting the muscles in the back of the lower leg. So he's doing leg lifts. We need to find the angular acceleration produced given that the mass that he's lifting is 10 kilograms at a distance of 28 centimeters from the knee joint, and the moment of inertia of the lower leg is 0.9 kilograms times meters squared, and the muscle force is 1,500 newtons with an effective perpendicular lever arm of 3 centimeters. So how can we actually start approaching this? Well, we can write down everything we're given. We're given that we're lifting a mass that's equal to 10 kilograms. So that's kind of the mass that we've got basically strapped to our leg. And the distance of that mass from our pivot point, the radius of the mass, is equal to 28 centimeters. So it's 28 centimeters away from the knee. The moment of inertia of my leg, I of the leg, they give us is 0.9 kilograms times meters squared. And the force that my leg needs to apply to actually keep this thing lifted up is equal to 1,500 newtons. And the radius of that force, so we'll call that RF, has to be equal to 3 centimeters. Okay, so what does a picture of this look like? Well, we have our knee joint right here, and then we have our leg. We're actually going to need to take this and let's shift this down a little bit so that we have a little bit of space to draw for this leg. So I have my leg, and I've got a mass kind of attached to my leg. We'll imagine this is the mass that's attached to my leg, and there's going to be a force acting on that mass. The weight is actually pulling me down. So that's the weight of the mass, and that's going to be applying some torque to kind of rotate my leg downwards around this pivot point of the knee. And it's acting to do this all at a distance of 28 centimeters. This is all given in the original problem. Now, to keep this leg from rotating downwards, I need to apply inverse torque to keep everything static and nice. And that inverse torque is provided by an upward force from a muscle in my leg, and that force is equal to 1,500 newtons. And I apply that force at a distance of 3 centimeters. So based on this picture, I can solve this whole problem. I'm looking for the angular acceleration. So I need to figure out how to use all these numbers to get angular acceleration. So to do this, I look at my picture. And this picture that I see has some rotational motion associated with it. The weight is going to make my leg kind of rotate around, kind of rotate downwards, rotate clockwise, and my force that my leg exerts to keep the weight steady is going to rotate counterclockwise. So it's going to generate some torques. So I can turn to torque to figure out the answer to this question. And I know the torque from Newton's second law, in the rotational version of it, is equal to I times alpha. And there is the alpha that I'm looking for. So if I shuffle this around, do some algebra, I can find that alpha has to be equal to the total torque acting on this leg divided by the total moment of inertia of this leg. And now if I can figure out this torque and I can figure out this moment of inertia, then I can get my alpha. So to figure out my torque, I need to look at what kind of torques I have acting. Well, I have a force due to my leg muscle actually bringing this up. So I have this torque. This 1,500 Newton force is creating a rotational force that's going to keep my leg going up. That rotational force is going counterclockwise. So by convention, that'll be a positive torque. So that's going to be R of the force that I'm applying times the force of my muscle times the sine of the angle between the two. But then I need to look at what other torques I have. My mass, this mass that I'm holding up, has some weight to it. And that's going to be pulling me down. That's going to make me want to rotate, make my leg want to rotate clockwise. So that's going to be a negative torque. So I need to subtract off the torque from my leg, which is going to be the radius where my leg is, times the weight of my leg, times the sine between the two. And now I can plug my numbers in. My torque is equal to the radius where the force is applied, which is going to be equal to 0.03 meters. So we convert that centimeters into SI units, times the force of the muscle, which is going to be 1500, times the sine of the angle. These are at a 90-degree angle. These are perpendicular, so sine of 90 is 1, times the radius of my leg. And I know that the radius of the leg, where the weight is actually being held, is equal to 0.28 meters. And that was given in the problem, times the mass of the leg, which is 10 times 9.8. So that comes from the weight, which is equal to m times g. And again, sine of theta is sine of 90, which is 1. So I can combine all of this to get a torque. I combine these torques to find that the total torque acting on this leg is 17.6. Then I need to find the total moment of inertia. The moment of inertia is going to be the moment of inertia of my leg plus m times r squared, where r is r of this mass. So that mass provides some inertia onto this leg. So the moment of inertia of my leg, I was given that, is equal to 0.9 plus the mass that I'm holding up with my leg, which is 10 kilograms, times the distance, the location where I'm holding this mass, 0.28 quantity squared. I plug this into my calculator. I find a total moment of inertia of 1.68. So I can take all of this, and we can shrink all of this down, and we can finally get our alpha. Our alpha is going to be equal to the torque that we just found divided by the moment of inertia. So alpha is the torque of 17.6 divided by the moment of inertia of 1.68. And when we plug those numbers in, we'll find an alpha of 10.4 radians per second squared. So that is probably the most difficult example of rotational motion that you would be expected to do on some kind of an exam. But it's very applicable for those of you that might be going into PT or some kind of health field.